Nikhil is going to start.
Can everybody hear me?
Yes.
Great. Hi, I'm Nikhil Krishnaswamy from Colorado State University, and my student and co-author Sadaf is fortunately there with you. I'm delighted to be introducing our paper, Detecting and Accommodating Novel Types and Concepts in an Embodied Simulation Environment, and the two of us will be sharing this presentation. Next slide, please. So first we'll introduce the problem, we'll talk about the environment that we use and the data that we have collected to perform this task, and then we'll talk about how we analyze the similarity between objects based on their behavior. We use a transfer learning approach to accommodate new classes when new objects are introduced in environments. We'll then talk about how we can use similar techniques to infer abstract concepts that adhere across multiple objects. Then the second suite of experiments we will present is going to be detecting novel classes when a novel type has been introduced into the environment, inferring how the agent can do that detection on its own. And then we will conclude with final takeaways and some future directions. Next slide, please. So as humans, we efficiently seek out informative experiences, and we were able to learn from few samples looking at previous examples. In particular, young children are very good at this. Meanwhile, artificial neural networks require large numbers of samples to train, and some recent research has found that it takes about 5 to 8 layers of artificial neurons to approximate the computational power of one cortical neuron. So the point here is that neural networks are not known to be easily expandable to accommodate new concepts given just a few unseen samples. So in this paper, we examine the ability of machine learning systems, and in particular, how we can design a machine learning system with the appropriate data and training and heuristic mechanisms to detect and acquire new concepts through an agent interacting with objects in the world. This is a metacognitive process, and in particular, this is a particular type of metacognitive process that's really just about the agent reflecting on its model and determining when the model is inadequate to the situation it's encountered. There's a lot of things that go into metacognition. We're looking at a particular narrow scope of one aspect of metacognition. So not pretending this is a general metacognitive agent, but want to define what we mean here. And for tractability, we focus on a domain of object interaction, in particular, the one that's inspired by geometric children's toys. So the objects that we will be looking at here are these common blocks, spheres, cylinders, capsules, an egg, a rectangular prism, a cone, and a pyramid. These are things that you might expect a toddler to play with. So, Sadaf, I'm throwing to you now.
So our environments are based. Can you hear me?
Yeah, you're good.
I'm good.
Yes.
Our environments are based on Voxboard platforms, and an agent would play with the objects. There are two objects. One is a destination object, the other one is a team object. The destination object is always a cube, but the team object can be one of the instances of 8 other objects. We do have two agents. One is a stochastic, the other one is a real agent. The stochastic agent, the agent would try to stochastically and randomly place one cube, one instance of objects on top of the cube. If the resulting configuration would be stable, the team object would stay still. Otherwise, it would fall off. In order to have a more realistic environment, we try to add a jitter derived from object semantics in VoxML for our object placement task. And in general, distinction in object behavior corresponds to habitat and affordances. And in our experiments, we show this through a stacking task. In our stacking task, we try to gather 10,000 samples for each object instances. And in general, our goal is to predict object type from its behavior, and we record geometric features of object interaction and configuration. The first thing that we try to examine is how our objects are similar, and this analysis would first start with predicting the object type, We train 4 layers feed-forward neural network, and this feed-forward neural network consists of leaky ReLU activation function, weight decay of 0.01. We use Adam optimization, and we train for 200 epochs. We perform multidimensional scaling on final layer, on final hidden layer activation function to capture the similarity across our objects. And we could confirm through MDS analysis that with objects with similar behavior lie close to each other in the MDS embedding. To explore more sample of efficient models, we use transfer learning approach, and we want to see what features are most important and what concepts has the network model to make the type distinctions. We begin by training a deep feed-forward neural network architecture on 3 objects, and those objects would be cube, sphere, and egg only, and we use 5,000 samples. We add 1 object at a time to the object vocabulary in the target model. So basically, our source model would start with 3 objects that would capture abstract properties such as flatness, roundness, and axis of rotational symmetry. During the process of transfer learning, we try to we freeze first 2 hidden layers of source model, and we add new hidden layer after the last hidden layer of our source model. Like I said in the previous slide, we try to, the first source model that we train would be included with egg, cube, and a sphere, and we add 1 object at a time. So the next target model would be cylinder, the next target model would include rectangular prism, the next one would be cone, next one would be capsule, next one would be pyramid, and the final target model would include a small cube while having the other objects as well. We compare the performance between the dynamically growing model and equal size static model, which is a 10-layer model. And in our experiment, the dynamically growing model identifies the 9 objects better and has a better performance. It also worth to note that during transfer learning procedure, as new objects would be added, the number of samples per object needed for fine-tuning would go down. We also try to infer abstract concepts. In general, our objects are not just instances of some multiple classes. It includes properties and contrasts that would exist across our objects. We have both round objects, such as the sphere and egg, and we have flat objects, such as rectangular prism, cube, and so on. And there are objects in our environment that would have round and flat properties, such as cone and cylinder. The data that we would collect would contain rotation of object after action, and this would have direct correlation with the round and flat edge of our object. We do our transfer learning approach to make inferences about abstract properties such as flat and round, and for these we split our cone stacking and cylinder stacking data, and we split them based on resting on the round edge and resting on the flat edge. We do the same fine tuning procedure to the previous 10-layer model that we did for object detection. Our model would be able to classify the round and flat concepts with the accuracy of 100%.
So, so far we've had a model that has had a fixed object inventory like neural networks would be expected to do. But if the agent is being driven by a machine learning model that has this fixed label inventory, how can it detect when a novel type has been introduced? This is a particular weakness of neural network approaches. So we try to exploit the stacking data to detect when new samples have come in that are not covered by the models that exist in the opposite that exists in the model. So to do this, we have all the intuition that it's pretty easy for, young children, for example, can infer when an object stacked on top of another one will stay still versus when it will fall off. And this is pretty easy to train a reinforcement learning policy to do. So we start there. We train a TD3 policy to stack blocks, and there are three training reward plots here. We have a maximum reward of 1,000. So when the reward is close to 1,000, the agent has successfully learned to stack the objects. We'll focus on the accurate policy, which is very well optimized, and the imprecise policy that is slightly more noisy. And these two policies are then used to generate more data. Next slide, please. So we focus on a subset of objects that we think preserve the concepts that would be important to detect when new objects have occurred. So if we use the policy trained on stacking blocks to stack a variety of objects, this is tantamount to making the agent stack all the objects as if they were cubes, because that's all it knows how to do. We then store the similar geometric information about each attempt, including the rewards now this time. And so you can see from the different reward plots on the different object types, there are some clear distinctions. Cube is very stackable, so is the small cube. Sphere is really not stackable. Capsule is kind of stackable. Cylinder is also kind of stackable, but not as much as cube. So let's see what distinctions we can automatically make using this data. Next slide, please. So the data is now time sensitive in that we give the agent 10 attempts. And so if it stacks successfully the first time, the episode terminates. If not, it gets up to 10 attempts to try to stack the object. So now there's a sequence. We train a 1D CNN classifier on a subset of these objects, and we start with just the cubes and the spheres. What this means then is that when a new object is run through, a new object sample is run through this trained model, it will be classified as one of those objects because it doesn't know anything else. What we do then is we retrieve the embeddings, in this case, 64-dimensional embeddings for the object samples and compare them to similarities with known objects whose classes we know. This now makes it an outlier detection problem in that the known object samples will form a subspace in the high-dimensional space, and if a new sample falls substantially outside of that subspace, it's probably an outlier. And so we set about trying to quantify that. The math is in the paper, but to cut it short, we basically define a threshold, and if we perform some math based on the mean and standard deviation of embedding vectors, and if a new object sample falls beyond the threshold of dissimilarity with the most similar object, it's considered to be a novel class. So here in these two charts, we can see information on the accurate policy data and the imprecise policy data using data that includes the object jitter that Sadaf mentioned and data that does not include the object jitter. And so when the model is provided with cubes and spheres, if you look at the chart on the right with that information that's derived from the Voxml semantics, it's very able to determine when a new object, a capsule or a cylinder, is in fact a novel class, while taking small cube to be an instance of a known class that is cubes. Next slide, please. Including the Voxml jitter information, because that is derived from information that includes the axis of symmetry of the object and other factors, this results in an impressive performance boost. So if you look at aggregated outputs over the dev test set, on the left, we see samples or the confusion matrix for data that does not include the object jitter. And on the right, you see the confusion matrices for the data that does include that. And so when we include that information, we can very easily correctly identify capsules and cylinder as novel types, while small cube is not a novel type. Without this implicit encoding of the habitats, we see that cubes are often confused with cylinders, and spheres are often confused with capsules because they otherwise share pretty similar behavior. And if you don't have that implicit information about the object habitat, you can't really distinguish them from the numerical data. Next slide, please. So in conclusion, a model should be able to detect when it's inadequate to the environment. This is going to be a robust and important capacity for robust intelligence in the future. We have found that no individual component, that is the neural network or the environment model or the statistical metrics, can bear sole responsibility for our ability to do this. This is somewhere in the combination of the hybrid approach and these approaches. So we're going to be conducting some tests to see, where this capacity kind of really lies in this hybrid architecture. We were able to expose key concepts, say flatness and roundness, through the stacking task. But other concepts, let's say that the cylinder doesn't have a point where the cone does, that might require other tasks to expose. So in future work, we're going to work on combining the two suites of experiments, the transfer learning and the novel class detection, by detecting that an object type is novel and then automatically expanding or fine-tuning the model to accommodate it for the future. We see a proposed integration architecture here on the right. One trick is that representations from different classifiers need to be aligned for direct comparison. Otherwise, the embedding spaces are such that they're basically non-overlapping. And so we have some linear modeling techniques that we're using to explore alignments between embedding spaces. Another future angle of research is taking outputs from the novel class detection and sending them backwards into the reinforcement learning task, where the RL policy can detect when it fails because a new object has entered the environment and then be adapted for. Next slide. And that is all. And with that, we would be happy to take questions.
Hi, Nikhil. Sorry, the microphone was not used. Neat stuff. And I think you already know what a question I will ask. And that is, you detect the new concept. This is great as from my point of view, as a preliminary step. But then you need to interpret them and categorize them with meaningful features. So, well, how do we do this?
Hi, Sergey. I thought that was you. I just couldn't tell until you turned the camera on you.
Of course, yeah.
Yeah, so one way of doing this is, topic of future work, one way of thinking about this is that if you look at, say, samples of cylinders that stacked successfully, they should be more like cubes, and samples of cylinders that were on their side and did not stack successfully should be more like spheres. How is that? This is kind of one of these flatness, roundness distinctions. If you look at the covariance of the embedding vectors, you will see that there are different dimensions where the cube samples and the stackable cylinder samples have a positive covariance, and then where the inverse is true. So then we are exploring, say, like training attention weights between the embedding vectors to try and isolate the dimensions where these covariances are highest. Then we have to, that doesn't really answer the question of grounding it to, say, a linguistic term or something. We have some preliminary evidence suggesting that you can actually use, say, a linear mapping from contextualized word vectors to the embedding vectors of objects. Now, this is just a very early experiment, so we didn't include it here, but there's some suggestion that that might work. Sorry, I can't hear you.
It's still preliminary. Right, thank you. So first, a terminological issue. The phrase transfer learning is an oxymoron. It doesn't mean anything. Classic term is transfer. Goes over 100 years back in psychology. It means improvement in learning. Transfer learning doesn't make any sense. I know that it's widely used. You don't have to use it, okay? Now the advanced and cognitive system community doesn't require that papers and talks be, report psychological models. But there is a bias toward papers that are roughly consistent with things we know about how humans work. And I got that you wanted to do that you were pushing things in that direction. But given that, why in the world would you start from neural nets when there are already models of categorization that do the kinds of things that you're talking about, that can handle new categories? I'm thinking about things like back in the early 90s, John Anderson had a Bayesian model of categorization, category learning that did this. Fisher's Cobweb does this kind of stuff. And there's a recent extension to Cobweb that deals with pixel-like data. So why would you turn to neural nets? Is it just they're sexy, or do you have a good theoretical or technical reason for this?
Sure. Yeah, that's a good question. And I think like you, I'm also a bit of a neural network skeptic, which is sort of where this came from. And so it's well known that neural networks are not good at this.
I'm more than a bit, but okay.
Sure, fair enough. So it's well known that neural networks are not good at this. And so the question was, is there a way to perhaps create some of this capability in a neural network architecture? And then if so, can we then in future correlate that to some of these well-known psychological models?
Why would you start there? That's my question. Why not start with something that we already know has these capabilities? It's been in the literature for decades.
Sure, no, I understand where you're coming from. I think
Like an answer though. Why?
Why? I think it's because we know this is not something that neural nets are good at. And so rather than, maybe this is a difference of culture between you and I, but I think we start from the challenge, right? We know it's hard, so we start there.
Thanks for the talk. I think it's interesting. So I have a question. This is Dustin. So you talked about that. So you talked about flatness and roundness, and that if you wanted to learn more concept like those, you would need to maybe add new tasks. I like the stacking task. I'm wondering if you were to add a dimension. So there's like the shape dimension, and you have all these different options. What if like weight mattered? And so now that was like a new concept, and all of a sudden you got objects that varied by weight. Would it just be that you maybe needed a different task, or would there be something like you needed to scale some of your components, or you needed to add other things? Like, just wondering how you might handle that. If the architecture, can it just scale if you have more tasks, or do you need something more fundamental in the system?
So I'll start, and Sadaf, feel free to jump in if you feel you want to add something. The easiest way is if we were to cache out more parameters in the virtual environment. So for example, if there's a way to measure if the weight of the object were encoded, and there's a way to extract or cache out information that numerically would correlate with those distinctions in weight, then that might be something that the architecture could learn. That's maybe something of a naive supposition, because sometimes the task would necessitate a different action space in order to expose those distinctions. So let's say if we had an object that was like asymmetrically weighted, right, then it wouldn't stack symmetrically anymore, right? And so making the same assumptions about the best place to put the object is on the center of the destination object would no longer hold. So the nature of the task, when you look at what children must know in order to learn other things, there's maybe some evidence that they have to know about certain motor control skills to learn how to stack in the first place, and then if they learn how to stack things, that might teach them other properties of objects. And there's a whole lot of between what kids do versus what computers can do. There's a lot of distance there, but the nature of the task that is being used to expose the numerical data, that's going to be the limiting factor in what kind of numerical data you can actually get. So that's kind of where the necessity for different tasks may come in.
Thank you. We are almost 15 minutes over now overall. So we'll thank the speakers again for this session.